Here's an overview of two energy changes for systems when it comes to chemical changes and also physical changes. We have exothermic changes and we have endothermic changes. Exothermic, since exo refers to outside or leaving, heat will leave the system or exit the system. Endothermic is the opposite, heat will enter the system. So we have these reaction energy diagrams. Sometimes we abbreviate reaction as RXN, but effectively it just means before and after. So here's what it looks like. For an exothermic reaction, it's going to start off with a higher energy and it's going to end up with a lower energy. This change here, this change from the high to the low, that is the delta H. And notice how it's negative. It's pointing in the downward direction, which means that heat has left the system. So it's going to be a negative change in the enthalpy. The opposite is true for an endothermic reaction. So for an endothermic reaction or phase change or something, we're going to start off with a lower amount of energy, and then relatively speaking, it'll end up with more internal energy. That means that we're going to have a positive delta H. So delta H is going to look like this, which means it is a positive change in the enthalpy. We often use the letter H for enthalpy, which for most basic purposes at constant pressure and such, it's basically just heat energy. Let's take a look at two examples. First one is hot coffee. If we have hot coffee, we want it to stay hot, but naturally, some of that energy is going to radiate from that hot coffee, and that's going to cause it to cool down. So the coffee had more energy, and then it's going to end up with less energy. It's going to cool down, and then it doesn't taste as good because we want our hot coffee to be hot. The opposite of that is when we have iced coffee or something cold to drink, and we want it to stay cold. What happens when the energy is moving into the system from the surroundings? It looks like this. So we have these little waves of heat energy, and it's entering the system. So it started off with a lower energy, and then as it melts and it warms up, the ice melts and the drink warms up, it becomes higher in internal energy. So that's effectively what endothermic and exothermic means in terms of those diagrams. In chemistry, it's important to understand how all this works in the context of chemical equations. So suppose we have two substances, A and B, and they react to form a compound, AB. They may also release heat while this occurs. So let's just use a dummy number like 100 kilojoules. The thing to pay attention to is the fact that the heat, the specific value and the unit for energy, which is kilojoules, or one of the units for energy, that's on the product side. So not only did this reaction produce the compound AB, it also produced or got rid of, so exothermically produced 100 kilojoules of heat for every 1 mole of A reacting with 1 mole of B. The key is that you'll see heat on the product side for exothermic reactions. Now let's flip that for an endothermic reaction. Let's say that we have CD, and in order for CD to break apart, we have to put some energy in. Let's use a dummy value of 150 kilojoules. That is going to produce C and D. So what's different here? We see that the heat value, so in this case, kilojoules as the unit, is on the reactant side. So we have two things going on. Heat on the product side for exothermic, because heat is produced. And then we also have heat on the reactant side for endothermic when heat is required. When it comes to these potential energy diagrams, you might just see negative delta H, or the fancier way to write the literal same thing is delta H less than 0. Because if delta H is less than 0, if the change in enthalpy is less than 0, it's negative. Over here, we might see a positive delta H, meaning we had to add in heat energy. But the fancier way to write that is delta H greater than 0. They're the same thing, just different ways to write it. This is a fancier way to write negative. This is a fancier way to write positive. Now let's flip these equations into a format that tells us the same information, but formatted just a little differently. So we have A plus B, and it creates AB, and not part of the equation, but separate from the equation. Like if you press tab once or twice, you'll get delta H, and we still have the same value here, but we do notice that it is negative. So it would be negative 100 kilojoules. It's telling us the exact same thing. It's just two different ways to write it. Two different ways to write thermochemical equations. Same thing over here. We have CD, and we can take the heat back out of the equation, so CD decomposes into C plus D, and when that happens, so press tab twice in your head, we have delta H is equal to, now you don't have to put the positive sign, but it's good practice at first, 150 kilojoules. So again, another way to write the exact same thing. Now let's practice identifying whether a certain phase change is endothermic or exothermic, as well as reviewing what that phase change term is. When you see S after a substance, that means that the substance is a solid. When you see an L in parentheses, that means it's a liquid, and when you see G, that means it's a gas. So for the first one, we have solid water, which we call ice, turning into liquid water. That's just melting. So we would typically call that fusion in chemistry, even though in everyday life we call it melting. And in order for a solid to melt into a liquid, we have to add energy in, so that's an endothermic change. Here we have solid carbon dioxide, which we would call dry ice, and it's turning into gaseous carbon dioxide, which means it's going from a lower energy state to a higher energy state. This would also be considered endothermic, and when a solid turns directly into a gas, we call that sublimation. Here we have gaseous water turning into solid water, so that's the exact opposite of sublimation. That term is deposition. Now, when we have a higher energy substance, so water vapor, and it has to turn into a lower energy version with the same substance, then we have to take energy out, and that would be exothermic. Liquid gallium turning into solid gallium, so liquid turning into solid, we would just call that solidification, which is also known as just freezing. And in order for a liquid to turn into a solid, we have to remove energy. That's also exothermic. Here we have liquid water turning into gaseous water. So liquid water is lower energy than gaseous water, so we have to put energy into the system to do that. And you know that if you ever put water on a stovetop and you boiled it, we would call that vaporization. And then we have liquid nitrogen turning into gaseous nitrogen. So if you've ever seen liquid nitrogen, what's happening there is it is vaporizing, turning from liquid to gas, just like we saw above, except it's a different substance. So it's vaporization of liquid nitrogen, still going to be an endothermic phase change. Here we have solid water, which is ice, turning into gaseous water directly, skipping over liquid. We saw that that term is called sublimation. And the substance doesn't matter, it's still going to be an endothermic phase change. And then here we have gaseous water turning into liquid water. And that's going to require a higher energy state to turn into a lower energy state. So that's going to be the removal of energy, so exothermic. And when gas turns into liquid, we call that condensation. So that's a review of the phase changes and connecting it to what endothermic and exothermic is.